So, there's this really cool piece of tech called Zynq. And even if you haven't heard the name, there's a really good chance you've used something powered by it, maybe even today. In this explainer, we're going to pull back the curtain on this revolutionary chip and show you how it's shaping the future of, well, just about everything, from cars to cameras.
All right, to get started, let's play a little game. What do you think three very different pieces of technology, say a military-grade radio, a professional broadcast camera, and the driver assist system in a new car, what could they possibly have in common?
The answer? They are all built around a family of powerful and super versatile chips called Zynq. Now, these are a special kind of chip, known as a system on a chip, or SoC for short. And their unique design is what makes them absolutely perfect for these really demanding jobs.
So what's the big deal? What makes Zynq so special? Well, it all comes down to its core design, a truly hybrid architecture that gives it a massive advantage over other chips.
But before we get too deep, let's just quickly nail down what a system on a chip actually is. It's pretty much what it sounds like, an entire computer system, the processor, the memory, all the interfaces, squeezed onto a single tiny piece of silicon. It's literally a complete computer, just miniaturized.
But here's the thing, Zynq isn't just another SoC. It's a total game changer because it was designed from the ground up to combine two very different worlds of computing. The predictable, fixed world of a standard processor and the infinitely flexible world of programmable hardware. All right, let's break that down. A Zynq chip is basically split right down the middle into two distinct halves, the processing system, which we'll call the PS, and the programmable logic, or the PL. And honestly, getting your head around this split is the absolute key to understanding what makes Zynq so powerful.
So, on one side, you've got the processing system, the PS. Think of this as the traditional brain of the operation, a powerful ARM processor, a lot like the one in your smartphone. It's built to run an operating system and software. But on the other side is the programmable logic, the PL. This is completely different. It's more like a set of super powerful custom-built muscles. It's a totally blank slate of digital building blocks that an engineer can wire up to create any specialized hardware circuit they can imagine.
This diagram shows it perfectly. You know, how these two halves live together on the same chip. That section labeled processing system, that's the fixed part with the ARM cores and standard stuff, and right next to it, that much bigger area labeled programmable logic, that's the magic, the blank canvas just waiting to be turned into high-performance custom hardware. Now, if we take a closer look at that processing system, you'll see it's way more than just a CPU. It comes packed with a whole bunch of standard hardware for talking to the outside world, all managed through this central hub called the multiplexed I/O. And we're not just talking about a couple of things here. You get USB ports, gigabit Ethernet for fast networking, SD card slots for storage, a whole range of standard serial ports for talking to sensors and other gadgets. It's a complete I/O toolkit, ready to go right out of the box. Okay, so you have this incredibly powerful and flexible chip. Awesome. But how in the world do you actually program it? You can't just use one tool for this. The answer is a specialized toolkit that lets you design the hardware and the software parts separately and then brings them together.
So the design workflow is neatly split between two main applications. First up, you have Vivado. That's your hardware design suite. It's where you configure the PS and, this is the important part, build your custom circuits in the PL. Then you have Vitis. This is where you write the C and C++ software that's going to run on the processor in the PS.
Now here's where it gets really clever. It's how these two completely separate design worlds, the hardware from Vivado and the software from Vitis, are brought together so seamlessly. It follows a really logical process. The flow is actually pretty straightforward. First, you design your whole hardware system in Vivado. When you're done, Vivado spits out this one single hardware description file, called an XSA file. Then you switch over to Vitis, start a new software project, and just point it to that XSA file. And bam! Just like that, your software environment knows every single detail about the hardware you just built. And right here, you can see that magic moment in action. On the left, you can see the designer is selecting that .xsa file that came from Vivado. Now look at the image on the right. Vitis has automatically filled in all the project settings because it now knows exactly what processor you're using and every custom hardware block you created. It's amazing. That little XSA file, that's the indispensable bridge connecting the hardware and software worlds. You can think of it like a digital contract that perfectly describes the hardware for the software developers. It details every custom piece, every memory address, every connection,
making sure both halves of the system work together perfectly.
Okay, so let's zoom out. Why go through this whole process of designing both hardware and software? Well, because it unlocks a level of performance and flexibility that's just impossible to get with a processor all by itself. It lets you turbocharge the parts of your application that need extreme speed.
And this really sums it up. Zynq gives you the best of both worlds. You get the familiar comfort of software programming on the processor, combined with the raw parallel power of custom hardware. For example, a normal processor might really struggle to decode multiple 4K video streams at the same time. But with Zynq, you can build a dedicated video decoding pipeline right in the hardware of the PL that handles it without breaking a sweat, leaving the main processor totally free to run the user interface.
This whole hybrid approach just blows the doors open for innovation. It lets designers build systems that are faster, more efficient, and way more capable than ever before. Which leaves us with one last, pretty exciting question to think about. With a reliable processor for all the complex tasks and a completely blank canvas for high-speed custom logic, all on a single chip, what could you create?